Hello, I'm Channa Bankapur. I've been solving daily challenge problems in October LeetCoding challenge every day and then posted a video in our YouTube channel, GoMaster Coding Interviews. If you see here, I have a playlist of 23 videos of the last 21 days in October. Take a look. So the intention of this one is to encourage people to code every day, and that's more like a workout for any computer science professional. All right. So today there are two problems. One is regular problem and another one is like a premium problem. So I have solved both, and in this video I'm going to explain my solution to both of these problems. Right. So the first problem is minimum depth of a binary tree. The problem definition is very simple. We need to find the minimum depth of a given binary tree. Minimum depth is the number of nodes along the shortest path from root to a leaf, right? It is the shortest path from root to a leaf here, not any other node. So in this example, the shortest path is going to be 2, right? Because it's going to go this way, right? So there is 1 and then there is 2 nodes in this path. So 2 is the shortest path. There are other paths like now this one, which is going to be 3, right? Because there are 3 nodes in this path from root to a leaf. If we have some other nodes like this, suppose there is 8 here and there is 6 here, this path 2 is not going to exist, so it's going to be 4. So therefore the shortest path in this case is going to be 3, and that is the minimum depth of this binary tree, right? So how do we find something like this? We can use depth first search or breadth first search, but breadth first search is going to make more sense. The reason is, say if you search level by level, right? This is level 1 and this is level 2. So when you're searching in level 3, you come across a node which is a leaf. So the whenever you come across a leaf, the first leaf you come across is going to be the shortest one, right? Is one of the shortest one from the root, right? And that is going to be the answer. So this 3 is going to be the answer, right? That's why I'm going to use this. It's a breadth first search. It's going to be a classical way of applying the technique. So here is my code. Most of it is like a skeletal breadth first search code. So if you see here, I have just handled the base case here in this statement. Otherwise, I'm going to start with level 1. So root is at level 1, and then I push the root to the queue. So as long as queue has something, we are going to process. But if you observe, this while loop is going to we come back to this while loop once per every level. So we are at level 1. Root is at level 1, right? So inside this level, we are going to find the number of nodes that are present in the level we are processing. So for the level 1, there is only one node. For the subsequent levels, there could be more than one nodes, right? So we are going to just loop over the number of times that the level has, right? The number of nodes in the level we have. So this is that counter we are counting down and then running it so many times. So within this one, I take up each node. So this is that node. And then if that node is a leaf node, we are done, right? Because this is the first leaf node we find, and that level number is going to be the answer. I'll return here and done with this problem. If not, I'm going to push or enqueue these the left and right children of the node so that they are going to be processed in the next level, right? So that's what we do in these two things. All right. So otherwise, outside of this while loop, I increment the level number because once per every level we do this part, right? So if it is a valid binary tree as an input, so at some point we're gonna get a leaf, right? And so we'll return from this one. This is the only exit point. I have written this one just for completeness, but this is unreachable code. All right. So it should work, and let me submit and see if it works properly. Right, so let me run the code for a sample test case, which looks good. Let me submit it, and then things look okay. It accepted, right? If you want to know the time complexity, it's not different from a classical breadth first search. But if you want to know more details about this one, let's look at what happened here. So we are going to run this while loop once per every level, and this one once per every node in that level. So that's why this part of the code is going to be executed once per every node in the tree. And look at this, all the operations in this part are constant time, or put together it's constant time. That's why we are going to run in big O of n, where n is the number of nodes in the tree, right? Which is linear time, and that is the lower bound for this problem. So this is the best we can do, at least in terms of asymptotic complexity or big O notation. All right. So I hope this is clear. If you know any other way of solving this one, let me know. I'm going to move on to the next problem. So the next problem is search in a sorted array of unknown size. Uh, so this is, there is a sorted array. We need to search for an element called target, right? Looks like a standard binary search problem, but one catch is we don't know the size of the array, right? That means it could be of any length, right? It's not infinite. There is some finite length, but it's not known, right? Okay. As usual, if the target is found, we are going to return the index of that. If it is not found, we are going to return -1. So this is as usual, just that we don't know the size of the array. So how do we solve this one? How do we get over that, right? Because normally a binary search is applied if I know the size is n. So if I know the size, I can start within a range of 0 with less than n, and then we can search within this range, right? But I don't even know what is n. So now to find n, actually we can apply binary search before that, and search that, right? So search for this n. How? Because look at this. There is an interface they have given. The interface is if you give the index, it's going to get me the element back. It is as good as reading the array. But if this index is out of bounds, then it's going to return some invalid, as in something which is not a valid value in an array, right? So this value is basically a largest positive integer in a 32-bit signed integer representation. Like normally this is represented as int max, right? So this is what it's going to return. But we don't know the size. Now we can apply binary search, because you can think of this as an array of infinite size, where there are some values which are lesser than int max up to n, first n locations, and from nth location onwards this value is stored. So it's as good as just searching binary search, apply binary search to find this element itself, right? The first occurrence of that index is going to be n. So we can actually find that. All right. So even to apply binary search on that, to find n, we need a range which is going to be 0 to some high value, which is higher than n, right? Greater than or equal to n. But how do I find this high value, which is just some index which is greater than or equal to n? Some random, it could be anything, but how do we even find that? So we need a little trickier method to even find that. So that's going to be the first stage. So this is a three-stage solution I'm explaining. Let me go through the solution I have designed with the code. That should be easier to understand. So the first stage is I'm going to find that high point so that I can find n. This is just to find the range where n exists. N is the size of the array. So I'll start with low as 1 and high as, so low as 0 and high as 1. We know there is at least one element in the array. So that's why low is always pointing to a valid element, uh, at least to start with. And high is basically that it's going to be, so we need to see whether uh, finally we want to make sure high is basically goes beyond uh, beyond that n or more, right? So how do we do that? Every time we check whether high is pointing to that n or more. So as long as it is not pointing to that, I'm gonna keep incrementing it. So but I don't increment linearly, I double this one. This is a way of doubling high value. It's as good as multiplying by 2. I'm just left shifting by 1 bit. So I also keep track of the previous high value as low, so that I have a range which is not starting from 0. It could be 0, but I'm starting from here. Suppose if n is something like say 40, then high is going to stop at say 64, but low is going to be 32. So this is my range now, right? So I can find 40 in this range. So that's the idea I'm using. So now this is going to take some login time to find high and low. So yeah, this will take big of log and time to find that high point, high and low both. And high and low is the range where n exists now. So I need to find n. I'm applying a binary search as if I'm searching for this element, right? Obviously, there is no element greater than this. That's why I'm searching for this element, the first occurrence of that. So if you know the binary search, this is going to work in a typical way, and we are going to get the that low is going to point to that n. So that's why n is going to be that this value. This is again a classical binary search, which will again take big O of log n time. Now comes, so now we know n, now we know the range which is 0 to n here. So we can find the target within that. So this is the standard binary search. Actually, there is a question which appeared in the daily challenge few days back on a classical binary search. I have made a video and then uploaded. So there must be a link somewhere at the top of the screen. So please click on that and watch that video to know more about a classical binary search, right? But otherwise here I'm just applying classical binary search to find that element, target element. If target is present, finally this low and high, both of them are going to point to that, right? So, but if target is not present, it's going to point to the smallest value which is greater than the target, right? That's what it does. If the target is greater than the greatest value in the array, it's going to point to n. N is beyond the array, right? So that's what it happens. So now what we need to figure out in this case is, so once we get low, we need to see the unsuccessful search. And for unsuccessful search, either low is pointing to that beyond the array, which is n, or whatever it is pointing to is not equal to target. It is slightly greater than target. In that case, I'm going to return -1. Actually, I don't need this first condition in, at least for this problem, because anyway, if I just get the low of that, that is not going to be target, right? That's that int max value we're going to get, right? So yeah, but otherwise the successful search is we're going to return this low, right? So this is the successful search. All right. So this is a classical big O of log n time taking algorithm. So now all the three stages put together, it's only three stages. So 3 times of log n is still log n. That's why the overall time complexity is still big O of log n, right? So we can search for an element in a sorted array of unknown size in big O of log n time. All right. So let me as in we already know the time complexity of the method I'm discussing, but let me still run this one and show how fast it runs, right? So it works for the sample test case. Let me submit and then it accepted, right? So we already know the time complexity, and if you see there, yeah, this is pretty fast, right? So 28 millisecond is pretty fast for this. All right. So if you know any other method, or if you want to discuss, please put down in the comments. Otherwise, please like the video and subscribe to the channel and go through other videos in this October LeetCoding challenge. All right. Thank you for watching. Happy